I don't know about you, but I've thought about life beyond our Earth for a long, long time. I guess I first started thinking about it when reading Flash Gordon comics back in the 30s, and we've had a lot of at that time we had very little thought that we could ever reach the moon, or that we could go by spaceships to Mars and so forth. That was just sort of beyond our, and also thinking of life on other planets. We knew about our own planets and so forth, but we've learned a lot more about the universe since then. And today we're going to be talking with Richard Schmidt about life outside or in outer space. So, Richard, thank you very much for coming on today. And let's start with talking about what do we mean by life in outer space? Do we mean Homo sapiens, or do we mean bugs, or do we mean worms, or do we mean trees, or what?
We'll start with bacteria. How about that?
Even bacteria, okay.
Yeah, or even small things like that, like amoeba.
Yeah.
I mean, amoeba is life. And so we had to define what life was first. And then, now that you know what the definition is, you know what to look for. So NASA came up with a definition. I'll read that one. It says, a self-sustaining chemical system capable of Darwinian evolution.
Okay.
Well, okay. But if you really boil it down, there's other definitions too. If you boil it down, you start out with an organism that has been born. Okay? If it hasn't been born, you don't have it. Okay, you got inanimate objects like a knife or a fork or something like that. It's dead. It doesn't get born. Yeah, you make it. But
somebody had to make it.
Somebody had to make it. Okay, but
and it wasn't the
life is produced from a prior generation. Okay, so reproduction is one of the requirements for life.
Okay.
If it can reproduce something and this thing can grow, how does it grow? It needs some food. So one of the things that we look at for life is something that takes in food, metabolizes it to create energy. That energy enables it to do activities, to grow, to reproduce. And eventually, these things die, but that's okay. We'll get fossils to indicate, oh, there was once life. So we even look for fossils when we're out looking for, was there life? Or is there life?
So it would be, take Mars for example, if we found a fossil on Mars, that would be a great find, wouldn't it? Because that would say we really had life on Mars.
We're trying to find out, has life come from inanimate objects, such as molecules or even elements, by itself, somewhere else in the world or in the universe? The only example we have of life is here on Earth so far. Okay. We haven't really found anything elsewhere.
And if we take a look at our own solar system, we have some planets, but we're so small compared to the rest of the universe.
Yeah, we're a tiny speck.
I mean, are we even a speck? If you want to really be humble.
We are here, okay? And so that's a starting point. We're here.
That's right, we're here.
And we got all
life.
The planets going around our sun.
Okay.
And then we look out and we say, is there another sun? Well, by golly, there is. Those suns we call stars. When we look out there, we start counting the stars, and we say, boy, there's a lot of them.
So each star is a sun, is that?
Every speck in the sky, you see that little speck in the sky that stays there. If it's moving around, it's probably something closer. If it's not moving, it's pretty far away.
Yeah.
Okay? And so those little specks are stars. Well, not necessarily. It could be galaxies that are even further away.
Okay.
Okay? But we're going to concentrate on things a little closer, the Milky Way. In the Milky Way, 100 to 400 billion stars.
Lord.
Fantastic numbers, okay?
And so many people, how long has it been since you've seen the Milky Way?
Well, I guess a couple of months ago I probably looked up and said, oh, there it is.
I don't know how long it's been since I've seen the Milky Way.
Yeah, it gets washed out from light.
It's the light pollution.
Yeah,
we don't really see the stars and the Milky. And
you get out in the rural area, now you can see it.
Yep.
Yeah.
And I remember being able to see it so clearly on our farm. You know, it
Oh,
was
yeah.
so well defined, and all those stars up there. But it's been a long time.
Yeah.
But anyway, within our own solar system, we have some planets. What's the likelihood of having?
Well, that's
some
it. I
life
started
on
looking at each of the planets, and I said, Mercury, not much chance of finding life there. Yeah, maybe we'll find something, but
It's so close to the sun. It's
so close to the sun,
hot.
very hot.
Yeah.
So you get to Venus, and you say, well, that's hot too. But they're saying if you go up high enough in the altitude on Venus, it gets Earth-like temperatures. Weird chemicals are there, so if there's life, it would be a different kind of life than we see here. Life doesn't have to be exactly like us, just as long as it satisfies this idea that, it looks for food, consumes the food, turns it to energy. Energy allows it to reproduce and to have some other activities and grow, that kind of thing. So we could find life that is strange, but it could be life. And then you get to Earth, and what do we find on Earth? Well, we found strange things called extremophiles, things that are living in acid, living in asphalt, living in other crazy places, too hot for normal life, but abnormal life can live there. So even on Earth we have a strange variety.
Well, we have all sorts of life on Earth.
Yeah.
We have flora and fauna. We have
Yeah.
we have the single cells or double cells or whatever it might be.
And
All the
figure it all
elements
started with single cells, and then they grew into multiple cells and just kept on evolving into more and more complex things.
Okay.
And we look at Mars and we're saying, hey, Mars is the closest thing to Earth in habitability. And so we're looking for fossils there because back in the old days of Mars, they're saying there was a lot of water. And water sort of produces life and aids it along. And so we're looking at Mars and saying, can we find some fossils? But we're also looking to see if maybe there's life there still. There's water there on Mars if you go deep enough down. You got ice caps on the poles of Mars. And so, maybe there's some sort of life.
Can you
today.
imagine the excitement at NASA if we discovered a fossil on Mars?
How? I mean, that's what you're looking for. We only have one example of life, and that's here on Earth. If we're looking for life elsewhere from inanimate, if we find some evidence on Mars, that's a big thing. But maybe you're going to find it on some other places. One of the funny things I came up with was this dwarf planet called Ceres.
Oh.
It's in the asteroid belt, and it's got a water vapor atmosphere. Who expected something like that?
Now, where does Ceres fit within the planets, or how far
The
away?
asteroid belt is between Mars and Jupiter,
Okay.
and so somewhere there is this big glob, and it's got an atmosphere. Surprise, surprise. At least it was a surprise to me. I hadn't heard of that before. Well, that's what happened. You start looking into these things, you get surprises. Then you get out to the big planets. The big planets are gas planets. They're mostly gas, but they do have rocky cores or some sort of solid cores. And maybe there's something there. Well, again, you'd have to go up in the atmosphere to find out something that could do it. But they got moons.
But it's very cold there.
Well, you're getting pretty far away from the
sun.
sun, yeah. But it turns out that the heat inside the core of these planets can help get the temperatures up there, And also, these planets that go around the large planets, these moons that go around the large planet, there's gravitational movement of the moons, and that friction creates heat. And so if you can find water on these moons, maybe you'll have life similar to what we found on Earth. And so we're looking at that kind of stuff. Saturn's the same thing. Jupiter, Saturn, they both have that kind of a gaseous planet, but moons going around them. Saturn has 150 moons. Jupiter, I have a number down for Jupiter, 79 moons. Wow, lots and lots
That's
of
a
moons.
lot of moons.
A lot of moons out there.
A lot of romance.
And
all the moonlight. They can have moonlight almost any time, I guess.
That's Uranus is a funny one. It's instead of spinning around like this and going around the sun, here's the sun and spinning around like this, it spins around this way.
Oh.
It's a funny one.
So it has the pole always looking at the sun?
Yeah, the pole always looking at the sun.
Oh.
Isn't that weird?
Yeah.
And so that's a little different.
And a pole never seeing the sun, I gather.
That's right.
Sort
the
of
opposite side is dark.
Sort of like the moon and the earth, since we never see the far side of the moon.
Very similar to that. Yeah. But again, it's got possibility of water. Now, how in the world you get water when you're that far away from the sun and the temperatures are so cold? This is one of the coldest planets out there. But again, the moons can have some internal heat from this gravitational activity. And they're saying you can actually find water on some of these planets. That, they'll have a crust of ice, but down below the ice, near the mantle, where the mantle is warm, you can have some water.
Okay.
Weird. And so Uranus has 6 large moons and 27 known moons. And you sort of concentrate on the large moons rather than go to the smaller ones. Neptune, we get out there to the furthest planet. Pluto got demoted from planet to dwarf planet. So Neptune becomes our furthest one out. And even there, you find, they're saying there can be on Titan, one of the moons, there's 14 known moons. Titan's the largest one. A frozen world that spits out particles of nitrogen ice and dust from below its surface. And they're saying even there might be some water, liquid water.
Now we haven't we used our space satellites or the vehicles that we've used to explore space? Haven't we seen all of the planets from one of the space?
Every planet has been seen close up by at least one of our
that's what I thought.
Spaceships that have gone out there. Even Pluto. We had New Horizons, I think it was called.
Yeah, it was New Horizons.
They passed
that's
them
right. Yeah.
and took some close-ups of Pluto and its moons too. Okay. Pluto has 5 known moons, and Charon is the big one, I believe. Charon is the largest one. Its diameter is over half that of Pluto. So now you got two really big guys, and as they rotate around each other, the Pluto is actually moved back and forth so much that it's outside the center of rotation.
Oh, okay.
And so that's a little different.
Yeah, sure is.
Usually your moons don't tug at the planet that much that the planet moves so much. Well, this one is so big. It actually moves.
And they must be fairly close. Well, they're fairly close together, too.
Fairly close together,
relatively speaking,
And so, again, you find water that far out. That's amazing. Okay? And let's see. After you go to those extremes, now we've gone out to the end of the solar system, what do you go after that? Well, you start looking at the stars themselves.
Yeah.
Well, those stars are way out there. Instead of being out there so many, a fraction of a light year to get to Pluto, you go out there 4 light years to get out to a star.
That's the closest star.
Yeah.
4 light years away.
4 light years.
And how many miles is that?
That had a lot of miles.
24 trillion miles, huh?
The numbers just get so big.
Huh?
That's why we talk in light years.
That's
so you
right.
can say, hey, 4 light years. You don't know what a light year is, but it's a big distance.
A light year, well, of course, the light year is the time it takes to travel, or the for a light to travel in one year. The light year,
right.
So it's 24 trillion.
When light travels an entire year, it has gone a huge distance.
Yeah.
And then we say, well, that's 1 light year. And then to get to the star, it takes 4 light years.
Yeah.
So you multiply that number by 4.
So that light we see from that star is 4 years old.
That's right.
Okay.
We're seeing old stuff.
And the light we see from some of the other stars that
further,
are way
much further.
We're talking about not just hundreds but thousands of light years away.
The study that produced more evidence of planets around stars is the Kepler spaceship.
Okay.
Or telescope, I should call it. The Kepler telescope. Do we have a? Yeah. Looking at the image on the screen, the one on the left is the image of the telescope itself. The image on the right is looking at the star. That's that big yellow thing is that star. And that little tiny black dot going across the top is a planet the size of the Earth going across. And would you know it's dimming the light coming from the star by just a tiny amount.
Oh.
And it's measurable. If you got a sensitive enough telescope, it can tell that the light has gone down 0.01% for a planet crossing in front of the star. If the star is sun-like, you know, it's about the size of our sun, and the size of the planet is about Earth size.
So we don't necessarily see that dot.
We don't see the dot. What we see is the light coming from the star dips, and that's what that little green line is. What they've got down there.
Okay.
It's like if you're looking on an oscilloscope and you see it going across, telling you the brightness, and suddenly it dips that 0.01%. And that's an actual photograph of what we can do. Okay. We've got sensitive equipment that can measure that 0.01%.
And this is the way we determine we have determined all of the exoplanets that we've discovered?
Not all, no.
No.
But a large number of them,
well, what's an exoplanet?
An exoplanet is a planet around another star.
Another star.
Not around our star. Anything around our star is part of the solar system. But anything around another star, we call an exoplanet.
And we discovered that in 1992, the first one.
Yeah, somebody got the idea, you know, if a planet is going around a star, the planet is pulling on that star. And so that star is going to wobble a little bit. And we can measure the wobble.
Oh.
Yeah. So that's what they did. For the first time in 92, they measured the wobble of a star. And they said, by golly, if it's wobbling at a regular rate, okay, now, if the planet is taking a year to go around, that's a slow wobble.
Yeah.
You'd like to find it wobbles a little bit faster, you know. Yeah. But even faster, maybe it's wobbling once a day. Yeah. Boy, that's a close planet, okay?
Sure.
And to get enough wobble, it better be a big planet. So large planets were discovered first, okay? But with this Kepler, we now can see not a wobble, but a change in the intensity of the light.
Oh.
And all the way down to the Earth size. Well, how long does it take an Earth to go around the sun? Hey, it takes 365 days.
That's right. Yeah.
So you got to be patient. Okay, so they set this thing up for 3 years. They say, okay, you're going to look at this star for 3 years.
Now, Kepler, though, looks at light, right? Whereas we have another one that looks at the infrared. Does that help pick up the planets? Is it Spitzer?
Looking at infrared is helpful for things that are very far away.
Okay.
If they're very far away, they're speeding away from us at greater speeds. As they go at greater speeds, it shifts the light into the infrared.
Okay.
And so having infrared telescopes help us study things that are very far away. Closer ones, well, infrared can go through dust easier than regular light. And so, yeah, infrared can help us on the closer ones too.
Well, how many have we discovered? How many exoplanets have we?
From the...
now, we first started,
right now, the number that I've got is 4,033 known exoplanets from all ways of doing it, whether you're measuring by wobbles or looking with a telescope and seeing something, or using the Kepler, okay? And there's 995 candidates of the, and they're probably from the Kepler information that they're still studying. And they're looking at that to see if, can we confirm from this mass of data that there's actually a periodicity going on. If there's a periodic change, we'll think that, well, it's going around the star and causing this periodic dimming. It's probably a planet, but maybe it's something else. Maybe it's something else coming in front of the star. Oh. So they have to check on all these possibilities.
So what we're seeing is not necessarily all the planets around a star when we determine that there's a planet.
Oh, okay. You're getting at the point that if you see it going across the star, that means its orbit is coming around sort of on edge on to you.
Okay.
If the orbit is slanted, you're not going to see anything going across the star. You're missing those. And the number that I came up with is about 200 to 1. So in other words, if we see 10 planets going across, we probably got 200 times 10.
Oh,
so
okay.
2,000 planets around that particular star. You know?
So in other words, instead of 4,000 exoplanets, we're likely to have...
You multiply by 200. Yeah.
200,000.
Yeah.
Yeah.
So I've got a plot, if they can bring that image up. The one before that, if we can get it. Yeah, that one. That shows all the planets that have been found. The red ones are the one from Kepler. The blue ones are all the confirmed planets. Okay, but the red ones are candidates left over from Kepler. The Kepler data has all these dots, these red dots there, indicating that we're still studying those. But the blue ones, those are confirmed.
Okay.
They have passed all the rigorous tests that they've come up with and says, yep, those are planets.
Now, is that 4,000 or is that the 995, the blue?
That would be the 4,000.
Okay.
And the red ones would be the 995. And you look down on the bottom, the period in days, we want to look out around 300, so you're between 100 and 1,000. You look there, and then on the left-hand side, the number 1 is Earth size.
Okay.
So you take the number 1 line and go out to about 300 and so on, and you see there's hardly anybody there. Well, if you go to the next slide, we expand that a little bit.
This is a logarithmic scale too, isn't it?
Yeah.
Yeah.
Because if you don't do it logarithmic, you get a really expansion here. So here they're showing the Earth line is the number 1 line. The number 4 line, 4 times the size of Earth, is Neptune, and 10 times the size of Earth is Jupiter. Gives you a feel for the different sizes of our planets versus the ones that they've discovered. And so you see all this crowd of blue ones that are previously known, and the yellow ones are the new ones that we've filled in.
Oh.
And you look out there, Earth is sitting out there at 365 days, and he doesn't have many guys around him, okay? And the size of him, not many around his size. A lot of them are bigger than Earth.
But if we look vertical around Earth, if we...
Yeah, you have some that are smaller, and then you have some that are...
But they're close to the size of Earth, if you look vertically.
Yeah, vertically, everything on the horizontal Earth line is the same size. Anything below it is tinier. Anything above it is larger.
But if you look vertically, then it has the same period.
Same period, yeah.
300 days or...
So you look vertically there, you see all the ones that are around
yellows,
1 year, 1 Earth year.
Yep.
And so you got a cluster of those too.
Quite a few.
Yeah. So I thought that was a very interesting illustration. The next illustration that comes up, if we can have that, we're going to find out that the heat of being close to the suns is just a small section that we can have what is called the habitable region. There we go. That tiny little square, if you can spot the square in the lower left corner of that blotch of red, is expanded up into that right-hand side, the big square in green dots. That's all been expanded up into that to show you from 200 to 300 Kelvin. Now, Kelvin is temperature relative to absolute zero. So 0 centigrade is 273 Kelvin, and that's over to the right-hand side of that upper chart. And so this is the habitable region. And when you stay particularly to the right-hand side, it's warm enough for water to be liquid. And you got the Earth size is number 1, and near the top of that section where all the green dots are is 2, which is double the size of the Earth. So in the 1 to 2 region, you got quite a few dots. Okay, so you got a lot of dots indicating planets similar to Earth in size and in temperature. But look at the rest of the red. All that stuff is hot, okay, because they're too close to the sun.
But what it illustrates is that there are planets that have similar characteristics of Earth.
Absolutely.
And we have lots of them.
That is the key.
Okay.
That is the key.
And now the next one that shows the mass and the radiant distribution.
Mm-hmm. We'll get that one up on the screen. It again will have on the left-hand side the radius and the radius of Earth being number 1, and then they'll have 2 and so on up as larger ones. And going across the bottom is the mass, and 1 is the Earth mass. So if you follow 1 up and 1 across, that's where Earth is. And that's sort of in the middle between the 2 dashed lines. The top of the dashed line is for H2O. That's water. So if the planet is all water, it would follow along that line. If it was made out of iron exclusively, it would fall along the bottom line. And sure enough, Earth is right in between those two. So we're not all water, we're not all iron. We got an iron core, but we have a lot of water.
Okay. And
so we fall in between the two.
All right, well, we're just about out of time, Richard.
Okay.
I think we need to sort of summarize, and we've got a lot of information about the stars throughout the universe, and we've got them many light years away. We've detected planets in there, so therefore we still have a lot of investigation to do throughout. And we're going to determine. We probably will not determine whether or not we have life on a planet for a number of years, and with just exoplanets.
Yeah, it looks like we're still a few years away.
We have detected that there are planets.
We're working hard.
We have detected that there are planets, and we know through the different ways that some composition of the planets.
Yeah.
But
we're going to look at the atmosphere around the planets. That's a tricky one.
But you know, it would seem to me that with all of the planets, and we're talking about, we said a couple of 100,000 in the Milky Way, and if we looked at the galaxies, other galaxies, we've got
billions,
or at least millions, billions. We've got there are Milky Ways that size.
Yeah.
So
a couple of 100 billion galaxies.
So the likelihood, as far as I'm concerned, is I look at the probability of life outside Earth. There's a much greater probability that there is life than there is that isn't.
It would be surprising if we're the only ones.
It would be very surprising.